Okay, so let's go over some of the homeworks I assigned from the review sheet. This is the final review sheet. This was from the traditional final. Our final is going to be slightly different. I'm going to tell you a little bit more about it when we get closer. Okay. Also, we're doing a lot of quizzes instead of for the final. So don't panic. Don't be too concerned with the final. Okay, whatever you've done during the quizzes is already going to count for quite a lot that we have done. Their quizzes are basically in terms of replace all the midterms that we were supposed to be doing. Okay, so the first one was it was just about convergence. So here is a series 9n squared over 3n to the fifth plus 5, and this was just convergent or not. And this was from n going to from 1 to infinity. But sometimes ask you, is it important where n starts from? And the answer is not really. Well, not at all. It's just sometimes if you take the wrong n, you might run into problems because the denominator might be 0 or something stupid like that. Okay, so what are we dealing with? So let me list again the possibilities. We have the integral test. We have the limit comparison test, the alternating series test, and then the ratio and also root test. But I'm going to mention all the ones that really matter. And so the question is it one of these? Well, clearly alternating series test is out here. What about the ratio test? It's a very strong and very good test, but there's certain types where it really doesn't work well, and this is one of them. And so we should really look here. This one, I hope everybody sees that is almost like a p-series, right? So I didn't write here the p-series and geometric series, right? Another reason that I would, so this I had already discarded. This one, I'm saying it could have been, but integral test, to integrate something like that, that's really horrible. Remember, we have a technique, this is called the integration by using partial fractions, but it would, for instance, involve factoring this bottom thing there, and that's, well, basically impossible here, or very hard to do. So integrating would be extremely long and hard, and so let's also put it out. I said, this one might look as something you could do ratio test, but if you actually do it, it's one of these cases where you get that the limit that you calculate is exactly 1, and that means that it's useless. So it will be a lot of work for nothing. But I'm saying all this, although I expect that most of you immediately see, oh, this is a p-series. It looks like a p-series, so I should do limit comparison test. So, sorry. So the one that I should look at here is the limit comparison. And then in the limit comparison, that's one thing we need to do is build a new series. And since we're building a new series, we can do whatever we want here, right? And so what we're thinking of is we take the highest degree of the top, but only the power, the coefficient is not important, and the highest degree in the bottom. That will be the bottom. And that's the choice we make. So then we take the limit. We show that to show that this choice is a good choice, you have to calculate this limit. And the way we do this is, again, a little bit different than what you normally would do, is we divide tops by tops and bottoms by bottoms. That is a valid operation. We get the same fraction as the original one. Why do we do this? Because we can now simplify. Well, this we can completely simplify. Be careful. You cannot cancel out within a sum. You have to divide everything by n to the fifth. So we get limit for n going to infinity. We get 9 on top, and in the bottom we get a 3 plus 5 over 9 to the fifth. Okay? And then, because we have 9 to the fifth in the denominator, if we put infinity here, this will go to 0. So we are left with 9/3. Now, this, or 3. This is bigger than 1, smaller than 1. What is the matter here? No, what we want is not 0 or not infinity. That's the only thing that we need. And then we are assured that the bn we chose is a good one. There might have been other bn's, but this is a good one. Okay, so now the last step that we do is then let's investigate Pn and write it really as a p-series, where remember p-series is in the bottom. So the power in the bottom is now 5.2 and 2, so p is 3, and that means which is bigger than 1, that means convergent. Okay, so that's it. Okay, these are rather simple questions, if you know what to do. Let's look at the next one. I also said AE, right? Okay, AE. That is summation n square over 2n plus 1 factorial. Now you say, oh, n square p series, right? But no, look at the bottom. In the bottom, this is again from 1 to infinity. In the bottom, this is a factorial. And with factorials, I have not seen any other case except where you have to do this except with ratio. Okay, ratio test. So we're going to do ratio test here. So ratio test. And for that, what we have to do, we take the limit for n going to infinity, and then, well, absolute values are not really necessary because everything is positive. We put the expression in the denominator. Please do follow this order as, okay? Don't mess it up. Don't get confused, because then you get exactly the opposite answer. And now we put in the top the same thing, but n replaced by n plus 1. And we use parentheses because we have to square something, and it's n plus 1 squared, and not n squared plus 1. And in the bottom, be careful here. Let's use parentheses again. So the n becomes an n plus 1, and then the whole thing between parentheses factorial. Okay? So what do we get? In the top, we get the n plus 1 squared, and the other fellow there this guy will go in the bottom. Let's work it out. That's 2n plus 2 plus 1, so 2n plus 3 factorial. Okay? This n squared will go in the bottom here, and this is in the bottom of the bottom, so after flipping it over, reciprocal, it goes in the top. Okay. There are two different things we do. The factorials, we know we can rewrite the biggest in terms of the smallest. This is the biggest in terms of the smallest, so 2n plus 3 factorial. That is 2n plus 1 factorial. That means, what we just wrote down means I have now multiplied all the numbers from 1 to 2, 3, 4, all the way to 2n plus 1, but I have to go all the way to 2n plus 3, and with steps of 1. The next one will be 2n plus 2, and then the next one will be 2n plus 3, and now only now I am where I want to be. Okay, so we have limit for n going to infinity, n plus 1 squared, 2n plus 1 factorial, n squared, and then we have 2n plus 1 factorial times 2n plus 2, which is 2n plus 1, we can factor that out, and a 2n plus 3. Okay? We can cancel these guys here. These guys will cancel out. And so what we have, we see an n plus 1 that can cancel with here, and now what we have left. Let's write down what we have left here. On top we have only n plus 1 left. And in the bottom we have 2, this 2, an n squared, and a 2n plus 3. I could, in this case, perhaps it's easier to see what to do if I multiply it out. You don't like to do this often, but in this case, because then I see the degrees. I want to see what the degrees I have. 4n squared plus 4n cubed, plus 6n squared. And so this is a limit of a rational function, and the way that we do this is by dividing top and bottom by the highest degree. Now we take the highest degree. That would be n cubed. And then look what we get. Okay, so we get limit n going to infinity. N, so I have to divide this whole thing by n cubed. So n divided by n cubed is 1 over n squared, and then I have a 1 over n cubed there. Then dividing this here, that will be a 4 plus 6 over n. Okay. Do this correctly, right? I need to see these steps, otherwise I'm not going to give you full credit. So this is 0, this is 0, this is 0. So what I get is 0 over 4, that is just 0. Okay? There are other ways that you could have solved this limit, but I'm just showing you one way. What does this now mean? Well, ratio test says it has to be less than 1 to get convergent. Okay? And then the last one, this was a question at 9D. 9D was, is it AC or CC? Or perhaps divergent. Okay, so 9D, what was that? Summation minus 1 to the n square minus n minus 1 over 2n square plus n plus 1. Okay, and this was again from 1 to infinity. Well, when a question asked about alternate absolute convergent or conditional convergent, it only makes sense, of course, if there are negative signs. Otherwise, it's automatically, if it's convergent, it is absolute convergent. If there are, because then taking absolute value doesn't change anything, so kind of a moot question. But in this case, what we always can do is do the alternating series test. Sometimes it's not necessary, but it's often also easier and kind of helps you already see what's going on. Okay, let's do this. Limit for n going to infinity. What do? You ignore the negative sign. Okay, this is now ignored. And we have n squared minus n minus 1 divided by 2n squared plus n plus 1. And we are back in an example of the same kind of type of limit here. So we divide everything by the highest degree, which is n squared in both. And so we get, this is the limit. For n going to infinity, we get 1 minus 1 over n minus 1 over n squared divided by 2 plus 1 over n plus 1 over n squared. And then all these reciprocals, because they become 1 over infinity, are 0. So we are left 1/2. That's less than 1. That doesn't mean anything here. Alternating series test, it's not 0, which means divergent. That's in fact what we call the divergence test. If this limit is not 0, forget it. These quantities are way too big. You cannot not add them all up. So does it answer our thing? Yes, it now completely answers our things, because if it's already divergent, it cannot be absolute convergent. We don't need to do anything else anymore. So that's why sometimes also pays off to first do the alternating series test. So the answer here was divergent. Okay, so I'll do a quiz on this, but I'm gonna do slightly more involved, and also, there was no problem here involving integral test, and I will always have something with integral test as well.